be about more about neural encoding. We previously discussed neural encoding when we discussed the concepts of firing rates and average firing rate and the spike count function, or spike rate function. And now we're going to build upon those ideas and also the ideas that we talked about in the tuning curves video to add a bit more complexity to how we model neural response with respect to some stimulus. So before we get into the advanced aspects of the neural encoding, I just want to give some intuition about the dot product. You've probably seen the dot product before. If you haven't, it's just a way to multiply two vectors together. So if our vectors are a comma b and c comma d, they're two-dimensional vectors, we just do the element-wise product, and then we sum the two products together, right? So the first elements multiplied together are a and c, a times c, and then that is added to the product of b times d. And then this is just some scalar quantity. It's not a vector, it's just a number that comes out of this. And so a way to think about the dot product and what this number at the end represents is that it's a similarity measure. It measures um, how similar two vectors are in the direction that they point to, right? This is an alternate definition of the dot product, aside from this this method of computing the dot product, which you take the components and multiply them together. The way to derive this is using the law of cosines. I won't do that here, but this is just another definition of the dot product that's equivalent, right? And so you can see that it's the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. Now we can ask, when is this quantity maximized? Well, u and v, or the magnitudes of those two vectors, are always going to be constant, right? Because this is just some set vector, and this is just some set vector. Um, these are just numbers, right? Um, the cosine value here is the maximum value of the cosine function is attained when theta is 0, right? Or anytime the like 0 plus 2 pi, and then multiplied by any constant, multiplied by any integer, right? So you want this theta here to be 0, and theta is 0 when these two vectors are pointed in the same direction, right? That's how we maximize the dot product. The dot product gets maximized when the two vectors of interest point in the same direction. Okay, so now getting into, we'll get back to actually using the dot product later, but in the last lecture we talked about tuning curves, and in these tuning curves we basically fit some sort of specific curve to the neural response, right? And so that was useful in the specific scenarios where our neural response neatly fits the curve that we had. But now we're trying to, if none of those things work neatly, if our neuron is acting a bit weird and we want to have like a customized fit to the neural response with respect to the stimulus, um, one naive way of doing that is to simply try scaling the quantity of the stimulus and then getting the neural response, right? Uh, so let's say this is maybe a volume of some sound that's coming into your ear. Then maybe you would expect that the neural response is just some scaled version of this, right? Multiplied by some factor. The problem with this naive approach is that it's usually not that accurate because neurons don't really respond to individual measurements of a stimulus, right? They don't respond um, in discrete time steps. What they do is they sort of aggregate a lot of information about a stimulus over some time interval. And if that time interval, if the stimulus over that time interval matches some sort of shape, then they fire. It's not always just going to be a continuous mapping. In fact, this almost never occurs. usually the neurons act as um, a sort of aggregator of the stimulus. And so it's usually not that helpful for the neuron to just blindly scale up the stimulus. This is usually not what happens. So this ends up actually not being a very effective method of neural encoding because it does not represent um, a large portion of neuron behavior. So what can we do instead? One of the most popular methods, and arguably the most simple, is the linear filter model, right? So let's say that a specific neuron of ours, a neuron of interest, only fires when the stimulus has this certain shape. It starts out kind of flat, it dips, and then it spikes, and then it returns to its original state. So basically, the neuron will respond only when this sort of shape is assumed by the stimulus that we have. And the stimulus could be anything, right? It could be visual, um, some representation, some numerical representation of what's coming into your eyes, ears, or even touch. And so basically, the goal, if this is the case, is to try to find which areas of the stimulus are similar to this feature, right? We're trying to see in the graph of the stimulus here, which areas of the stimulus look like this. That's essentially the basic question we're trying to ask. And so if you recall to our initial discussion of the dot product, the dot product is a good similarity measure between two vectors, right? And by calculating the element-wise, products and then adding all of those things together, we saw that that is actually a very good approximation for whether or not two vectors are similar. Well, it's not that hard to see that if you believe that's true, then you can also do that for functions, right? If you imagine taking the dot product of two functions together, uh, and I know when I say functions, there's infinite values on these functions. So imagine like lining them up against each other and then multiplying the corresponding values. Then it should also make sense that when those two functions are similar to each other, the resulting product and then the sum of all those products should be very high, similar to what we did for the dot product, right? And so that is where the idea of a linear filter model emerges from. Essentially, what we're going to do is take this feature, which is of some length of time, and we're going to take this graph, essentially put it everywhere on the stimulus and slowly slide it over, and at each time we slide it over, we do a dot product. We compute the element-wise products and then sum everything together. And once we do that, at each like sliding position, we'll get a value, and that value is R of t, our neural response. And so this is the discretized version of the linear filter. Usually in practice, you don't actually have continuous measurements, right? Because these instruments that we use to record from the brain, they'll record at certain time intervals, right? Like maybe every few milliseconds or so. And so this, in practice, we do everything discretely, in time steps. This is the theoretical approximation of this, but essentially what this is saying is here S of t minus k is a stimulus value, and f of k is a certain value of this feature here. And basically what we do is, given some t, we're basically trying to calculate the neural response at some time. And so what we'll do is we'll align this graph onto our stimulus function, a stimulus graph, and then we start off with k equals 0, and that represents the end of the feature here. And then we multiply this value with its corresponding value on S of t when it's all aligned up. And then we'll just keep computing backwards. Like we'll keep going backwards, and then we'll take this value, multiply with the corresponding value on S of t, take this value, multiplying with the corresponding value of S of t, and so on, until we do this for every single value of our feature of interest that we're trying to look for. And if at a certain point in the stimulus graph assumes a certain shape, the same shape as the feature, then the resulting product of the resulting product, like these values added together, will be high. And so that results in a high neural response. That is essentially what the linear filter model does. It looks for areas in the stimulus function where the feature is looking like uh, like the shape that we've defined this to be. It doesn't have to look like this. There are many shapes, and you can sort of choose the one that fits for your neuron. But using this, um, it basically finds where in your stimulus uh, the stimulus matches the shape of the feature. And using that, we can output neural response. One small note though, when we do that, when we use the linear filter model, it might be the case that sometimes the stimulus function or the resulting R of t value may be negative depending on the value of the stimulus, right? If the stimulus value, maybe we're measuring the loudness of some sound, if it's very high, um, that does not correspond to a proportionally high value for R of t, because as we know, neurons they don't adjust the the sort of intensity of each spike, right? The only way we can represent some high stimulus is by actually increasing the frequency of spikes. We do not ever modify the intensity of a single spike. And so all of the spikes, all the neural response function has to be bounded somehow. And the way we do this is by using a nonlinearity function. Here I've depicted one of the most commonly used ones called the sigmoid function. And basically what this is, for very high values, we approach a horizontal asymptote of 1. And for very negative values, we approach a horizontal asymptote of 0. And this goes on for infinity in both to infinity in both directions. And so by doing this, we essentially maintain the smoothness of the neural response function, and this is actually desired because it sort of accurately represents what's happening in the neurons. And we also are able to effectively put a boundary case, like we're able to bound the values of the neural response where it otherwise might not have been so. Another interesting sort of method of encoding, previously we were encoding neural response with respect to time. But another thing that you can do using a sort of filter that we discussed before, what we can do is actually do spatial filtering. So neural response may also depend on what, especially in visual scenarios, right? Um, it can actually depend on what you're seeing and where you see it. So your visual field or your visual field is basically can be represented two-dimensionally with we're using y and x, and if we define some sort of filter that's also two-dimensional, then we can take whatever input your eyes are seeing and then multiply each corresponding value in that input image with the same values from that two-dimensional filter. And then that also basically serves the same purpose that the previous filter did in the one-dimensional case. Here we're kind of extending the dimensions in that uh, our our filter is defined for both x and y coordinates, whereas before we were just going for the filter was just defined along the time axis. Here it's a bit more complex, but we'll see an example on the next slide. So a really popular example of a spatial filtering model is this specific filter called a difference of Gaussian filter. And this filter is used prevalently to model cells in the initial layers of your visual processing system, specifically the retinal ganglion cells. These cells they're kind of different from what we saw last week with the Hubel and Wiesel experiments. Remember the Hubel and Wiesel experiments, uh, the cells actually recognized sort of diagonal lines or bars of light that are oriented at specific angles. These cells in the initial layers are a bit more simpler than that, in that basically they'll fire if at their center, wherever these are located, whatever part of your visual field these are looking at, if the center part is bright and the surrounding part is dark, then it will fire. That's basically what this is called, like a center on, surround off cell. And so we can basically model this cell using this specific type of filter called the difference of Gaussian filter, right? So, these red values here represent high values for the filter, and then around it you have very low values. These are negative values. And so the way you basically define this, I didn't, you can kind of infer from the name. If you think of a Gaussian function like a normal distribution curve, it's just a one Gaussian distribution minus another one orientated in the opposite direction in the bottom. That's essentially how you create this sort of three-dimensional shape. And so essentially what this does is you can kind of imagine that if you're sliding this filter across a specific image, then if there's any areas where there are high values in the center and low values around that center point, well, that's exactly what this filter is trying to find, right? And if you sort of think about like the dot product similarity idea, and this is the thing that we're dot producting with, that we're dotting with, then the result we'll have high values for areas that match this sort of pattern, right? And so basically what this ends up doing is finding edges. So this is actually sort of, in this picture you can see, this is sort of the resulting image that we get after moving this filter across at every point of this image, right? And so if you take a look at which values are black, which represent values that were high when we used this filter, you can see that it has found all the major edges of the Taj Mahal, right? Here, for example, the high value could be the white edge of the marble, and then the other low contrast values would be around that specific area, right? Because there's a sharp contrast between the colors here. And so that actually activates this exact sort of shape, where there's a high value in the center and then lower values surrounding it. And so essentially this is a very sort of effective version of an edge detection algorithm. And it's pretty simple too. It doesn't take that much code to implement this up. All you need to do is define this filter, which is using some sort of numerical computation library like NumPy, for example, in Python. You can easily define this sort of difference of Gaussians, and then all you have to do is slide it across different different grids of this image, depending on the exact size that you're looking for. And so it turns out that this is actually a very interesting application of an idea that we kind of took from studying computational neuroscience and then apply it to the field of computer vision. And throughout the club, we'll actually see repeated occasions of this, where an idea from studying the brain was actually carried out to lead to advancements in the field of computer science. It's pretty cool. So the last thing we're going to talk about today is a bit different from the sort of um, models, the filter models that we've been discussing. Uh, we're going to be discussing something called a spike-triggered average. And specifically, all the other things that we discussed, including in the tuning curves video, which we did last week, and all the models that we discussed this week, we're specifically focused on modeling neural response with respect to some stimulus. But spike-triggered averages are a method of actually determining what stimuluses cause the neuron to fire in the first place, right? Like um, in order to create the sort of filters that we talked about earlier, we first need to know beforehand that the specific neuron that we're recording data from is looking for areas of an image like this, right? We need to define the shape first. And so spike-triggered averages are a very simple yet effective way to do that. And interestingly, spike-triggered averages are not just used in the field of computational neuroscience, but also they're used prevalently in like stock market evaluation, where where you're trying to figure out what sort of um, what sort of variable caused a spike or like a rise or fall in the price of a certain stock. And there's a huge number of um, use cases for it in addition to that. But yeah, let's get started. So as I mentioned before, the spike triggered average is used to determine what specific stimulus, like pattern, makes a neuron fire. And this can be used for any type of stimulus, um, including visual stimulus, auditory stimulus, or even touch, and many more. So this is the basic formula. Um, I'm going to actually discuss more about this using an example on the next slide. So imagine if we have a screen, right? And we're measuring um, from a cell in the later parts of our visual system, where this cell actually responds not to like individual, um, not like a simple response, like responding to a diagonally oriented bar of light, like we saw in the Hubel and Wiesel experiment, but actually this cell responds to certain complex patterns in this grid, right, in the screen that we're seeing here. And our goal is to figure out what sequence of patterns on this grid actually leads to a spike, right? What sequence of patterns causes this specific neuron to fire? And so what we can do is just randomly randomly generate noise, right? Random noise. This can be done by sampling from a Gaussian distribution and just randomly inputting these values, right? Um, at some point, if we keep giving different kinds of stimulus, eventually it will spike. And once we record this spike, or several of these spikes, after a trial that's uh, a certain time length long, it depends on the specific example that you're trying to do. But once you do that, you can go find where each spike happened, then move backwards in time where you look at what the stimulus feature the stimulus pattern was right before the spike, a little bit before the spike, and a little more before the spike, and then you can see by taking the so let's first figure out what we had to show the neuron uh, 0.2 seconds before the spike, right? We take all of the grid patterns that we saw 0.2 seconds before the spike. So here was one that we saw before this spike, and here was 1.2 seconds before this spike. And we take all of those that happened 0.2 seconds before a spike and simply average them up. And we get this, right? They basically represented this by summing up all of the white and black squares in this grid and taking the average of those. And then we do the same thing to figure out, okay, what do we have to show the neuron 0.1 seconds before if we want to see a spike? And we get this. And then we say, okay, right before the spike, or at the instant that the spike occurs, what do we have to show? and then we get this sort of very strong average. So this seems like what the neuron is looking for, right? This shape, where there's something in the top left corner. And so by conducting this sort of spike-triggered average, this method, we can basically figure out what type of neuron patterns cause our neuron to fire. And then you can imagine that if we're trying to perform neural encoding, given that we know that this specific type of stimulus pattern causes our cell to fire, we could then define a filter, like a spatial filter like we were talking about earlier with the difference of Gaussian functions. We could then define something like that here. And once we do that, we have our neural encoding model. So spike-triggered averages are a really cool way, a really simple way of figuring out what stimulus pattern causes a cell to fire. And this is just the formula here. So here Ti is the time of a certain spike, right? And if we have n spikes, that's what this variable represents. And then tau is what time before the spike are we looking at to average, right? So to get this grid, we would set tau to be, as mentioned here, negative 0.2 seconds. I mean, yeah, just 0.2 seconds before the spike. And then this would calculate the spike-triggered average. If we put in 0.2 seconds for tau, it would calculate the average sort of grid pattern that you see here. And so by inputting these values, we can actually create the spike-triggered average. That's what this formula basically says. And we average over all the spikes that we see, right? That's what we're doing here. And yeah, that's it. So thank you for watching. All the images in this textbook that were uncited come from these resources, and we hope to see you next week. Thank you.